Okay, so let's look at section 7.2. We're dealing with laws of exponents that apply to rational exponents, meaning we're including fractional exponents as well as integer exponents. Now remember that fractional exponents means that we're taking a root. So let's start by sort of doing a side problem, reviewing how to take a root. And let's look at the problem, the fifth root of a to the 8th, b to the 20th, c to the 82nd. Now, when I simplify a root, I use the idea of taking an exponent and dividing it by the index. And I think that's easiest illustrated with this kind of problem where we have variables involved. So looking at the a, our exponent on a is 8. The index of the problem is 5. 8 divided by 5 is 1, remainder 3. Now that says that an a to the first power gets to come out of the radical, and an a cubed remains underneath the radical. Looking at b, we would take 20 and divide it by 5, and that's 4, remainder 0. So that would indicate that a b to the fourth power gets to come out of the radical, and no b's have to remain underneath the radical. And then for c, we would take 82 and divide it by 5, and that would be 16, remainder 2. So that would say that a c to the 16th gets to come out, and a c squared has to stay underneath the radical. Now keep in mind we're taking a fifth root, so don't forget to put your index of 5 by that radical symbol. Easy to forget, but costly on a quiz or a test. And underneath we would have an a cubed and a c squared. So our answer would be a b to the 4th, c to the 16th times the fifth root of a cubed b squared. Now as a quick double check, look at the exponents that remain under that root symbol, because none of those exponents can be equal to the index or larger than the index. If they are, then there would still be work to do to simplify. So now let's look at some of the examples that we have, and keep in mind that when we write our final answer, it should be written in simplest radical form. So for problem 1, I have 7 to the 1/2 times 7 to the 2/3. Since the bases are the same, our law of exponents would say that we could add the exponents. So let's go ahead and do that. We would have 7 to the, now in order to add our fractions, we need a common denominator. That will be 6. So 1/2 would be 3/6, 2/3 would be 4/6. Adding those exponents, we would get 7 to the 7/6 power. Now at this point, I could actually do the kind of thing we did above, take the exponent and divide it by the index, because we actually see those. And that would give me 1, remainder 1. So that would say that my answer 1/7 gets to come out, 1/7 needs to remain under the sixth root, and my answer would be 7, sixth root 7. Now if you don't see the exponent divided by the index there, or you just prefer to work with radicals, at this point you could rewrite it as the sixth root of 7 to the 7th and take it from there in terms of simplifying. Looking at problem 2, I have 27 to the 1/3 times 6 to the 1/4, that quantity squared. First thing that I would do as I approach this problem is rewrite that 27. I know that I can write that as 3 cubed, and then I'm going to take that and raise it to the 1/3 power times 6 to the 1/4, and then I'll take the quantity and square it. Now the reason I did that is because when I raise to a power here, the 3 times the 1/3 is just 1. So I really have 3 that I'm now squaring. So I have 3 squared times 6, and then the 1/4 times 2 would be 6 to the 1/2. So now simplifying, 3 squared is 9. The 1/2 means to take the square root, so I take the square root of 6. 6 does not contain a perfect square as a factor, and so my answer is 9 square root 6. For problem 3, there are different approaches that you can take to do problem 3. I'll show you one that you may not have thought of, and then I'll show you the other. Either one is correct. It's all a matter of what you see when you approach the problem. So one way to do this problem is to say both the 4 and the 2 are being raised to the third power. So what we could do is rewrite as 4 times 2 the quantity to the third power and take that to the negative 1/3. At that point, we know that 4 times 2 is 8, so we really have 8 cubed that we're going to raise to the negative 1/3. Multiplying exponents here, we would get 8 to the negative first power, and a negative exponent means to take the reciprocal, so we would write that as 1/8, and that would be fine. What you could do is at this point you could take each of those and raise it to the negative 1/3 power. You would get 4 to the negative first times 2 to the negative first. That would be 8 to the negative first, and that would give us the 1/8. Now either way is correct. Again, it's a matter of what you see when you look at the problem and what seems easiest to you. So let's look at problem 4. We have the same base. We're dividing. So law of exponents would say if the bases are the same and you're dividing, subtract your exponents. So we're going to have 6 raised to the, in the numerator we have an exponent of 1, so we have 1 minus 3/4 power. That would give us 6 raised to the 1/4 power, and then putting that in simplest radical form, we would have the 4th root of 6. Looking at problem 5, I have the cubed root of 162. Now the first thing I'm going to do is go off to the side and do a factor tree on 162. I know that it is 2 times 81. 81 is 9 times 9, and each of those 9s would be 3 squared. So looking at the bottom row of my factor tree, I can rewrite the 162, the cubed root of that, as the cubed root of 2 times 3 to the 4th. And now I can simplify. I only have 1 2, so it has to stay in. I have my index of 4 here, so I take 4 divided by 3, that's 1, remainder 1. So a 3 to the first power gets to come out, and under the cubed root I need a 2 and a 3, and then multiplying them together I would get 3 cubed root 6. For problem 6, since the indices are the same, I'm taking the same root, I could actually multiply those numbers together and keep them under the cubed root. So one way of doing the problem, rewriting that 25 and thinking of it as 5 squared, that would give me the cubed root of 5 squared times 5. That's the cubed root of 5 cubed, which is just 5. Now, if you wanted, you could deal with fractional exponents, or you could multiply out, and instead of saying that 5 squared right away, you could say you have the cubed root of 125 and take that to the cubed root of 5 cubed. Either way would be correct. Again, it's a matter of what you see when you look at the problem. Now, problem 7. Problem 7 I have indicated as a 3-star problem. And I have that because it can be confusing at first, and also because you are guaranteed to see it on a quiz and probably your test as well. So you need to know how to do that kind of problem. Now, I notice a couple of things when I approach this problem. I have a variety of bases, and I'm taking different roots. So I am taking a 6th root and a 6th root, and then I'm taking a 4th root. Now when we first look at that, we might want to say, well, 5 goes into 10, I can reduce that. And yes, we can, but we can't do it in the form that it's in. So the first thing we have to do is rewrite that 10 and rewrite the 6 and think of them in different ways. So I know that 10 is 2 times 5, and then that quantity is being raised to the 3/4. And I know that 6 is 2 times 3, and that quantity is being raised to the 1/6, and then 5 is just 5, and it's 5 to the 1/6 power. Now, I'm going to raise to the power in the numerator, so I'll have 2 to the 3/4. times 5 to the 3/4 times 2 to the 1/6 times 3 to the 1/6 all over 5 to the 1/6. Now what that did, by rewriting the 10 and the 6, it allowed me to see the pieces. And even though they were taking, or they're part of different roots, I can use my law of exponents to say, well, if I'm multiplying, I add the exponents if the bases are the same. So with that 2, I can add my exponents. I need a common denominator, so 3/4 and 1/6, common denominator is 12, so I would have 9/12 plus 2/12 times, and then the 3 doesn't have anything to multiply it by. I could leave its exponent as 1/6, but eventually I'm going to need a common denominator for that. I'll just get it right away and rewrite that 1/6 as 2/12. Now the 5s, I'm dividing, and so law of exponents would say subtract my exponents. So the 3/4 will become 9/12 minus 2/12. So now I can do my addition or subtraction for the exponents. I would get 2 to the 11/12 times 3 to the 2/12 times 5 to the 7/12. So at this point I want to take a look at my exponents, see if I have any improper fractional exponents, because that would indicate that something can come out of the root, and I don't have any of those in this problem. So then I can say, well, the denominators are all the same. We purposely did that so that they are all under the same root, and that is the 12th root. So I would have 2 to the 11th times 3 squared times 5 to the 7th, all under my 12th root. So I would find the 12th root of, and at this point I would go to my calculator. I would take 2 to the 11th times 3 squared times 5 to the 7th, multiply them out. I would get 1,440,000,000. So my answer then is the 12th root of 1,440,000,000. Now as a quick recap for this kind of problem, first thing we did, looked at that problem, noticed that some of those numbers could be rewritten. We wanted to think of them in a different way. And that really is a key component of being able to simplify radicals, being able to think of things in a different form. So we rewrote the 10 as 2 times 5, we wrote the 6 as 2 times 3, raised all of those pieces to the power that was indicated. What that allowed us to do then would be to see the parts and be able to multiply those pieces that we knew we could multiply or divide them by using our laws of exponents. Once we did that multiplication, we checked our exponents to see if we had any improper fractions indicating that something could come out of the root, and then we put whatever remained under it and simplified by going to our calculator and coming up with a single number to represent that. So hopefully this problem, or going through this problem, helps. Make sure that you go and review it, because again you will see it on a quiz or a test.